So last time we guessed the radius part of the eigenfunction for this hydrogen atom coming from the Schrödinger equation. This capital R is given by this exponential decay when rho goes to infinity times rho to the power of L when rho approaches 0 times a polynomial capital H as a function of rho. We simply plug in this assumption or ansatz to the radius part of the Schrödinger equation, and we get the following form. Okay, so you can verify this by plugging this capital R back to the Schrödinger equation and the radius part. Again, so we assume that this H function is a polynomial in rho with infinite number of terms. Okay, so the coefficient runs from A0 to A infinity. Sounds very familiar because we have done that in the harmonic oscillator problem. Should find this so-called recursive relations, which is the relation between the coefficients of k for different k. Okay, so let's just plug in here. We get some relations. Right, so if you do the algebra, you see this very easily. Now let's just collect the terms that is proportional to rho to the power of k minus 1. So let's just find this coefficient in front of this power, rho to the power of k minus 1. So, and we could find the relation between a of k and a of k plus 1 or a of k minus 1. So let's do it. Right, so how to do that? Well, you just do the power counting. So this term is proportional to rho to the power of k minus 1. Good. And this is also, but this term is rho to the power of k minus 2. So then you need to shift your k so that you actually want to just focus on the rho to the power of k minus 1, and then shift this k so that you collect this term, okay, the same power as the other two, so that this k becomes what? K plus 1, so the first term. Okay, and the coefficient also shifts it by 1, so k, a of k becomes a of k plus 1. So that's how you get this term. Of course, k in this way, k cannot be, say, 0 because you get this meaningless term. But for k, say, greater than or equal to 1, so this relation holds. So now you know that this rho is proportional to the radius, the r, cannot be 0. So because the right-hand side of the equation is 0, the only way that you can make this, the whole series vanishing, is that this coefficient inside the bracket vanishes, right? And so that's how you get this relation between the neighboring a of k. This must vanish for all, because otherwise, if you get any finite terms for any k, the right-hand side will not be 0. Okay, so the 0 is very, very strong constraint on all the terms in this polynomial. In other words, all the coefficients on the left-hand side of this polynomial should vanish, which means that this coefficient of a of k and a of k plus 1 should be 0 for all the k's, which means that this a of k plus 1 divided by a of k is given by, simply just move this around, you get this. This looks messy, but for k is very, very large, say much greater than 1 or approach infinity, so you could just forget about all the other variables such as L and 1 and lambda. So all these are just some finite values. You only keep the leading term when k goes to infinity. So you pick up one factor of k in numerator, another 2 in the denominator, so it's k divided by k squared, and you forget about all the other finite parameters. As a result, in the limit of k very, very large, you get 1 over k. This tells you immediately that a of k plus 1 is approximately given by 1 over k factorial for very large k. Because ak plus 1 is actually ak plus 1 is 1 over k ak. And what is ak? Well, ak is what 1 over k minus 1, ak minus 1. What is ak minus 1? Well, this is, again, 1 over k minus 2, ak minus 2, and so on and so forth. You get this all the way to a0, so then a0 is simply just a constant. So this is approximately given by 1 over k factorial. So now let's use this result, plug this in back to this h polynomial, which is divided into two. One is the for small k. You still have this polynomial in rho, but for large k, you get different things. So you get this type of behavior. For very large k, the coefficient becomes 1 over k factorial. But what is this? Again, so in the harmonic oscillator chapter, we studied that. We have almost exactly the same type of polynomial that we discussed before. Remember, in the harmonic oscillator part, we actually rewrite this kind of k large part of the polynomial in terms of an exponential function subtracted by a finite number of terms that could be obtained by Taylor expanding this exponential function. This is nothing but e to the power of rho plus or minus some polynomial in rho, but finite, with finite number of terms. The only thing that we need to actually make an exponential function e to rho is that to actually add, this is the same as, so let me just write it down here. This is the same as sum over k from 0 to k bar, and k bar is the smallest value of k where we think that k is large, plus starting value k bar, which is the value we think k is large. But you add this term and you need to subtract the same term. You add the same term and you subtract by the same term, it's the same thing. But the advantage of doing this is to actually come up with the exponential function. So if you combine these two terms, then this is precisely the Taylor expansions of e to the power of rho. But the price to pay that you need to subtract the whole thing by the finite number of terms with this Taylor expanded terms coming from this e to the power of rho, but that's fine because this is just a finite number of terms. That will come in to this bracket that you need to subtract a finite number of terms in the form of the polynomial in rho. Of course, you need to also add this term, okay, the small k part of the polynomial. Okay, so there are two sources of the polynomial in rho at finite terms. One is the first part, another is a subtracted term that you did. But in any case, both terms contain a finite number of rho to some power as a polynomial in rho with a finite number of terms. That will not lead to any trouble. The troublemaker is the exponential function right here. So now let's just rewrite this h polynomial in terms of exponential, which is roughly e to the power of rho plus a polynomial in rho. this is what we can do at this point, and to find out what this h of rho is. So now we need to plug this in back to this ansatz. So back to this polynomial that we start with. So by starting this polynomial behaviors, this h of rho, and now we conclude that this is given by exponential rho plus polynomial rho at finite number of terms. So let's just plug in this back to this general solution of radius part of the eigenfunction. So this is e to the minus rho of 2 over 2 times rho to the power L times h of rho. And you could plug in this h of rho back to this capital R. You get e to the plus rho over 2 times rho to the power L plus some polynomial rho with a finite number of terms, which we don't care. The troublemaker is this exponential exploding terms, e to the plus rho over 2, and this term becomes infinity, as you know already, when rho goes to infinity. Precisely the same way that we argue when we discuss harmonic oscillator problem, right? So this h of polynomial in rho cannot go that many terms, so cannot be the polynomial with infinite number of terms. It should be cut off, okay? Because if you keep expanding this polynomial in the h of rho, you will end up getting this e to the plus rho over 2, because there is a factor of e to the rho and there's e to the minus rho over 2, so you got cancelled. But you still have exponent plus rho over 2 right here. And this is exponential exploding terms that will lead to meaningless results, because we know that wave function cannot explode. And in fact, it should vanish at infinite far away distance. When rho goes to infinity, this capital R, the radius part of the wave function, should vanish, but instead becomes infinity, so this must be cut off. We must cut off this h polynomial at finite number of terms to actually prevent us from being such a unphysical situation, which means that this h of polynomial must terminate. This h of rho at some point. Remember, we have the exactly same conclusion in the harmonic oscillator part. So this h polynomial should terminate at some point. We must cut this polynomial at a finite number of terms. That constraint or condition determines the energy quantization of a harmonic oscillator. Same thing happens here. So this truncation or termination of this h polynomial determines the energy quantization of a hydrogen atom. Okay, so let's take a short break. When we come back, we will start to discuss this termination of this h polynomial, the corresponding energy quantization.
这里的 k 是什么意思
？k 是一个整数啊，你的多项式 rho 的多项式的那个，应该说是它的 power 的编号啊。
它有物理意义。
等一下我们就讲它的物理意义。k 就是一个 integer， 你的多项式，高中数学不是告诉你的多项式是什么 ？a_n_x 的 n 次方，对不对？我只不过把这个 n 叫做 k 而已啊，这样明白吗 ？Okay, so let's terminate h of rho. To do so, let's go back to this h of polynomial. We get this relation previously. So when we plug in this h of rho back to the Schrödinger equation for this radius part, by plugging this ansatz, our ansatz. Here we are, so we get this relation among different prefactors a of k, especially the relation between ak and ak plus 1. But we need to truncate this a of k coefficient, because this is the way that we do the truncation. So the way that we do the truncation is that we should consider the finite number of terms in this h of polynomial rho, but say for up to k equals to capital N, so they are fine. But beyond that power, rho to the power of n plus 1. So for any terms that go beyond this finite number of terms in this bracket, we should make it vanish. But we know that rho cannot be 0. So rho is the distance, so the radius. The only way that we can make this polynomial vanish beyond a certain number of terms is by demanding that coefficient should vanish. In other words, we should make sure that all the coefficients beyond that power, rho to the power of n, should vanish. We should find a way to guarantee that all the coefficients that go beyond this certain number of power of rho should identically vanish. How do we do this? You could go back to the recursive relation right here that it says that there are two terms. One is ak plus 1 times those numbers, and those numbers are positive. K is positive integer, L is a positive integer, and plus 2, and all is plus. These two factors cannot be 0. And we don't know whether this ak plus 1 could be 0 or not. And suppose ak is finite. Only way that you could make this coefficient 0 is to demand that this bracket, which contains lambda minus L minus 1 minus k, this term vanish. But how could that be? Of course, it is possible because k is the positive integer, L is positive integer, and lambda is here is also a positive integer, which means that if lambda is equal to L plus 1 plus k, and we're done. So if lambda is the sum of the three numbers exactly canceled, this bracket actually is 0. Okay? So let's just assume that we could achieve this goal. So suppose we could do that. Suppose that at the particular term that lambda is precisely equal to that sum of the three numbers. And remember, the L is an integer. 1 is integer, k is integer. So the sum of all the three integers is still an integer. So lambda is an integer. Oftentimes we call this a principal quantum number. K is some textbooks is denoted by n of r. Again, n of r is an integer. So let me just, this is called n of r. Little n is called the principal quantum number, which is an integer which is made of the three integers, 1 and L and n of r. In such a case, we could show ak plus 1 vanishes, because if this is the case, we immediately see that k plus 1 plus lambda L minus 1 minus k, k 0. Suppose that this bracket vanishes to satisfy this recursive relation, so we must conclude that ak plus 1 is 0. All right, because this bracket dot 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 refers to k plus 1, k plus 2L plus 2, right? So both brackets are positive numbers. But this is 0. So 0 times ak is 0. And To satisfy this, you must conclude that coefficient ak plus 1 vanishes. Everyone gets that? But once the ak plus 1 vanishes, we could derive all the coefficients from this recursive relation. The coefficients beyond that power k plus 1 should also vanish. Okay, so the way that we show this is precisely just go back to this recursive relation one more time. But you simply just shift k by 1, say by plus 1. Suppose k is shifted to k plus 1. K minus 1 is actually k. This is k plus 2, k plus 3 plus 2l, a of k plus 2 plus the same thing, lambda minus l minus 1 minus k minus 1, and a of k plus 1. Still vanish. But this time, this bracket with the lambda here is non-zero, because we just demand that this lambda minus l minus 1 minus k is 0, but you get extra minus 1, so this bracket will not be 0. This is just minus 1. However, ak plus 1 is 0. Remember that. This is coming from this result, right? So ak plus 1 is 0. ak plus 1 is gone. So then you can look at this recursive relation, and to satisfy this, the only way that you could do that is by demanding that ak plus 2 is 0. Okay? So, and then you could go on forever. So this is just the case where you shift k by 1, and you could shift k by 2. K goes to k plus 2, and k goes to k plus 3 until k goes to infinity. For all the remaining power beyond k plus 1, you could take advantage of this recursive relation, conclude that all the coefficients that larger with k larger than k plus 1 should vanish. And we're done. So then this h polynomial is indeed contains finite number of terms from, say, 0 of k to k being n. So this k rho of k. That's it. So we accomplish our mission. But now let's look at this condition to terminate this h polynomial, and this is precisely this energy quantization of hydrogen atom. So let's just look at this consequence of this condition. And if you look at the definition of lambda, lambda is this one. So let me just repeat that. Lambda is actually n, and is what? Lambda is z e magnitude. Okay, remember in this case the eigenenergy should be negative, because remember this potential V of r is actually a negative value potential. And it's attraction between the electron nuclear core in the hydrogen atom. So this quantized energy levels should show the negative eigenvalues, and that's why we add this absolute value here to actually extract this magnitude of the eigenenergy. But now you could actually invert that relation to get exactly the quantization, the eigenenergy. You should remember to add minus sign here. This is the quantization for eigenenergies of a hydrogen atom, which is precisely the same form as Bohr's prediction. Remember the Bohr model, he considered a circular orbit of electrons around this nucleus cores with a particular angular momentum. And then from that quantized angular momentum carried by the electrons circling around the particular circular orbits of nucleus, you could derive such quantized eigenenergies. But here we don't go through this Bohr's semi-classical treatment, but we go directly by solving the Schrödinger equations, and we find exactly the same result. So the energy are quantized with the minus sign, and which is inversely proportional to the principal quantum number n squared. And this is a very important result. So let me just emphasize this quantum number, r plus L plus 1, and we know that nr is greater than or equal to 0. It is an integer. From this relation among all these different quantum numbers, and we know immediately that this principal quantum number should be greater than or equal to L plus 1, because nr is a positive 0 number, which means that this n is actually greater than or equal to L plus 1. And number 2, as we already mentioned, n is an integer, which is positive, because n takes the minimum value of 1. Suppose L is 0 and R is 0, this principal quantum number takes a minimum value of 1. Number 3, lambda is the same as n. So now you get almost everything for the hydrogen atom, because we know the eigenenergies. The remaining task is to find out their eigenfunctions. We know their eigenstates with particular eigenenergies. The next steps are to find out this quantitative features of these eigenstates, including the relations among all these different quantum numbers. You know very well that if you have different combinations of nr plus L, and you may come up with the same quantum number, and this is called degeneracy. Suppose you have two different combinations, nr1 plus L1 plus 1, it's actually nr2 plus L2 plus 1, but it turns out that in some cases these two combinations are identical. For example, if nr1 is actually 2 and L1 is 1, 2 plus 1, but I can revert that numbers. I can have nr2 being 1 and L2 is actually 2. 2 plus 1 plus 1 is the same as 1 plus 2 plus 1. Both combinations give you 4 as a principal quantum number, which means that you have two different states with the same principal quantum number. This is called degeneracy. And we discussed and we defined the degeneracy long time ago. Degeneracy refers to that there are multiple states that are different. They are orthogonal states, but they have exactly the same eigenenergy. In the hydrogen atom, we have many degeneracies for fixed principal quantum numbers. So we will discuss that in just a moment. Okay, so any questions? I hope this reasoning, the argument, derivations are clear enough, because we have studied harmonic oscillator. Everything that we did here follows exactly what we have done for harmonic oscillator. So let's take a short break. When we come back, we continue those steps. Just continue discussing this consequence of this quantized eigenenergies and eigenstates for hydrogen atoms. This is the very familiar spectrums for hydrogen atom that you must have seen this in, say, general physics, modern physics, that we have such quantized energy levels of hydrogen, which the quantized energy levels is actually eigenenergies are proportional to minus 1 over n squared. When n takes a small value, there are larger energy spacing between adjacent levels, but as n increases more and more, you get more compact, more continuous distribution of those energy eigenstates, so that this level spacing between adjacent energy levels are smaller and smaller. You really reach the continuum when n goes infinity, whereas quantum nature disappears. Remember, this mu here is actually reduced mass, which is this combination. Capital M refers to the mass of the nucleus. Little me refers to the electron mass. When you have this two-body problem, so the mass should be modified to actually this form. So then you must have calculated that before when you study modern physics or general physics, that if you have some excited state electron quantum particle staying, say, higher energy level labeled by I, but this particle is unstable because there is lower energy levels available, so that this particle actually decay into that lower level state J, but then this, because the energies are quantized, when this higher energy particles come down to the lower energy, and then there should be this radiation emitted by this kind of processes. Now the emission carry this energy h nu or h bar omega ij, and in the hydrogen atom, such a transition, say, energy or frequencies could be observed and calculated by this formula that we just derived. Okay, so the this kind of light emission with a frequency nu is related to the difference between these two energy levels, capital EI and EJ. Subtract from one another, you get this dependence. So it's inversely dependent on this n square. If you know this quantum number ni and aj, so you know immediately how much is energy of this radiation emitted. So this is just a standard spectrums of hydrogen atom. And so let's look at this degeneracy. As I mentioned, this refers to the fact that there may be many situations that you have different eigenfunctions or eigenstates, but they have the same energy. This is the case because you have the three numbers added together. So in particular, you have two unknown integers, L and nr. As long as sum of the three numbers are equal, I don't care whether this is 1 plus 2 or 2 plus 1. So because the eigenenergy depends only on this 1 over n squared, it doesn't depend on nr or L, so that you cannot distinguish all these different eigenstates with the same energy. Okay, so that's what we call this degeneracy. So this is an example of this degeneracy of the lowest energy levels of hydrogen atoms. For example, this ground state refers to the state where you have quantum number, principal quantum number m being 1, which means that both L and nr vanish. You have only one unique ground state. But when we go to the first excited state, which is n goes to 2, and we have 4 degenerate states. What are the 4 degenerate states? Little n is 2. We have two situations, as I mentioned. First one is nr is 1, but L is 0. And the second is nr is 0, but L is 1. Okay, because nr plus L plus 1 is the same number, 2, right? 1 plus 0 is the same as 0 plus 1. But these two situations are very different because in the first case, when nr is 1 but L is 0, remember the quantum number for this z component angular momentum operator ml can only take this single value 0, because ml, remember, is between L and minus L. Remember that. But when L is 0, L can only take a single value, which is 0. But when we have the second case and L is 1 and R is 0, then L could be minus 1, 0, or 1. But all the three different states are orthogonal and normalized eigenstates of the angular momentum operator L squared, the eigenstates of the Hamiltonian of a hydrogen atom. altogether you have 4 degenerate states. Okay, so these 4 states have the same principal quantum number. Therefore, they have the same eigenenergy. But these 4 states are different states, all different states. Why? Because they have all different quantum numbers. So if you look at this combinations of these 3 numbers, you'll see that they are all different. Although they have the same principal quantum number, but they have all different situations. So if you look at this, all these quantum numbers associated with these 4 states, you will see immediately that these 4 states are completely different 4 states. Why? Because although they have the same principal quantum number, which is 2, but if you just compare these combinations of the nr, l, and ml, there are no combinations among these 4 states that are identical. There's always some difference. For example, this 2, 0, 1, 1, it's different from 2, 0, 1, 0, and also different from 2, 0, 1, minus 1. Because remember, when ml shows different values, that represents different eigenstates. If you look at these 2 states with the same 0 of ml, but then they have different nr. Okay? So we will come back to this when we combine all these different components of these eigenfunctions. You see that nr also played a role in this radius part of the wave function. For example, the other states, like with ml being minus 1, so these 2 states, these 2 states are different because ml are different. So there are no 2 states with the same combinations of all quantum numbers. No, there's no 2 identical states. So all these 4 states are different. The only thing they are in common is that they have the same eigenenergy. That's all. Good, so we can go on to calculate this degeneracy, or number of the states having the same energy for n equals 3. In that case, you get what? nr2, nr being 1, and nr being 0. For nr being 2, L can only be 0. In that case, ml can only be 0. But for the second case, when L is 1, you got 3 states, with ml being minus 1, 0, and 1. And for the bottom case, when L is 2, there are 5 degenerate states with different mLs ranging from minus 2, minus 1, 0, 1, 2. All these states having the same eigenenergies, they are degenerate states for n equal to 3. What is the degeneracy then? Simply just sum of all the states, number of states, 1 plus 3 plus 5 equals 9. But then you immediately notice that 9 is actually the square of 3. Okay, so in general, you could really count number of degeneracies, and the number of degeneracies sum up to n squared. The degeneracy for the general principal quantum number n is actually n squared. So you could generalize this degeneracy formula to any arbitrary principal quantum number. This comes about because you sum over L from 0 to the L maxima. Inside the summation, you sum over, there are 2 L plus 1 degenerate states for each fixed L. As a result, when you sum over L from 0 to L maximum, but what is the L maximum? L maximum is nothing but n minus 1, because this relation here. So L minima is 0, but L maximum is what? n minus 1 when nr is 0. L minima 0, but L maximum n minus 1. So you sum over all possible L, but for each fixed L, you have 2L plus 1 degeneracy. As a result, this summation gives you precisely n squared. It's a simple algebra. Therefore, we learned a lesson that in the hydrogen atom, for principal value, principal quantum number, n fixed, there are n squared degenerate states. So let's just look at this wave functions or eigenfunctions. We know that this psi is given by capital R, which is a function of n and n r times y o n. And we know what is capital R function rho. This is given by e to the minus rho over 2 times rho of L, power of L, times this H polynomial. And therefore, the remaining task is to find out what this capital H polynomial is. And so let's do it for a simple case. Suppose that we look at this easiest possible excited state, which is the first excited state. When n equals 2, you get two situations. One is L is 0, but nr is 1. In that case, you could very easily figure out this H function. Simply just plug in this condition to this energy quantization conditions. You immediately notice this A coefficient. You very easily derive all these prefactors A of k. For n equals 2, this is very easy, so you only have two non-zero polynomial terms, with A0 is 1, but A1 is minus 1/2, and all the remaining A coefficients, AKs, are 0. Your H of rho, in this case, is simply just 1 minus rho over 2. This is for n equals to 2, L equals 0, and nr is 1. Let's take a short break. When we come back, we will figure out the other cases for, say, n equals 2 and also for n equals 3. Once we figure out the coefficients for this A of k, then we simply just know everything. So let's just summarize this H polynomial y over n for the lowest excited states of hydrogen atoms. So we just derived this when n equals 2. We have two cases. One is L equals 0 and nr is 1. In that case, this H polynomial is actually 1 minus rho over 2. Y over m simply is y0, 0. And the second case, when L is 1 and r is 0, if you look at this H polynomial, the coefficients, and so on, you find that this is simply just 1. But y over m shows three different eigenfunctions, y11, y10, and y1 minus 1. And for n equals 3, we have three different cases with different degeneracies. In the first case, when L equals 0 and r is 1, and there's just one unique state, this H polynomial is given by these three terms. The y over m is simply just y0, 0. In the second case, when L is 1 and nr is 1, you have three degenerate states. The H of rho is given by 1 minus a quarter of rho. Y over m is given by this 1, 1, 1, 0, and 1 minus 1 component of the spherical harmonics. The third case, when n r is 0 but L is 2, so you get 5 different spherical harmonics. I don't bother writing down this H polynomial. You could figure that out. We will come back later, so when we discuss how to remove the degeneracy. This is no accident. This is not accidental results that you have such a huge degeneracy. The fact that we have this very large number of degeneracy is because we have extra symmetry. And that symmetry, very large degeneracy, this is because our potential shows a spherical symmetry. And there is another symmetry associated with that. There is some conserved quantity because of the spherical symmetry. We will figure that out next time. This is just a remark to tell you that there is a reason for that. Let's just combine everything to look for these eigenfunctions. In general, this H polynomial has a name for that. There is a special function called this associate logarithm polynomial. This is denoted by this capital L with a superscript 2L plus 1 and subscript n minus L minus 1. So this symbol refers to that definition. Okay, anyway, so this is just some special function that you could derive by solving this differential equation for H polynomial. We don't want to memorize all this messy stuff, but this is just to let you know that in general we could get analytic, precise, exact solutions for this H polynomial. Okay, and there's a special name for that special function called associated logarithm polynomial. Of course, you have this results of H of rho in the simple cases, but in general, in the much more complicated, higher order, say higher excited states, and you could follow this associated logarithm polynomial to figure out the H function. Let us just write down the full radius part of the eigenfunction, which is written in our textbooks. You don't need to memorize all these eigenfunctions, but you just need to know that how you can derive all this radius part of an eigenfunction. So, and here A0 is a Bohr radius. This quantum numbers here refers to this n and L. So you could simply just plug in this radius part of the eigenfunction together with y or m, you could construct this psi of n L m, which is the eigenfunctions for hydrogen atom. So let me just write it down here. Point is the following. Suppose that I give you, say, some initial wave functions of hydrogen atom, and you could show that if you take the measurement of that initial wave functions, and what is the probability that you find this particle to be at particular eigenstates of the hydrogen atom. Suppose I have this initial wave functions of certain form of this, and you could calculate that if you take the measurement of this initial wave functions, what is the probability that you find this particle to be in certain, say, excited states with certain quantum numbers. In order to do so, you just need to make sure that you know this Fourier expansion theorem that we discussed long time ago, and then to use your knowledge in quantum mechanics as a probability distribution, okay, when you take the measurement or the wave functions. So you could, for example, if the initial wave function takes the combinations of all different eigenstates, and of course it's just out of second that you can figure out the probability that you take the measurement and you find this particle to be at certain angular momentum states, and so on. So, and this is the point, and therefore the points are not about to memorize all this complicated radius part of the eigenfunctions, of course, but then to be complete, for the sake of the completeness, so let me just write down these four solutions of this eigenfunctions of the hydrogen atom, which can be found in your textbooks. Okay, so this is the final answer for a hydrogen atom, that we figure out the most general eigenfunctions that satisfy this Schrödinger equation for hydrogen atom, which carry this radius part of the eigenfunctions, the angular part. And the radius parts of the eigenfunctions contain this special function called associated logarithm polynomial, which is nothing but h of rho, and you can show that this is a normalized eigenfunction. So let's take a short break. When we come back, let's just analyze the behavior of such a general eigenfunctions of hydrogen atom, especially the probability distribution of this psi and Lm along the radius direction, also in this angular degrees of freedom. We'll see all this electronic configurations that you studied in high school, such as s orbital, p orbital, and so on, and we should see such distributions from this psi square. Okay, so let's take a short break. Okay, so let's look at this spatial properties of this eigenfunction psi nln as function of rc times phi. You can actually plot this square of this psi, this entire spatial Euclidean, and from this combination. So this is the probability, say dr d omega, probability distribution of this electrons in the hydrogen atom. So in particular, suppose we simply just look at this radius part of the probability distributions. This is actually given by r squared times capital R squared. So you could plot this probability distribution in the radius part directions of this eigenfunctions, and you will see how this wave function is distributed, what's the shape of these orbits, and so on. For example, if you look at this r dependence of this psi for a small r, okay, so if the distance, the radius is actually small, and you can show that this is given by r to the power L, this really tells us the system would like to keep this psi of r staying small for a range of r for increasing L, because when L increases, this actually r to the power L is actually become increasingly smaller and smaller. So which means that this, for increasing L, this probability that you can find this particle at small distance is really, really tiny. If you look at the graphic representation of such a statement, is that this is your electron, so-called circling around this nuclear core, but with some radius r. But if L is very large or L is increased, then this radius part of the wave function depends on this r to the power L for small r, which means that you would never find this particle near the nuclear core. So if you look at the probability distribution of this wave function, this probability is almost zero when r is very, very small. Okay, which means that L is large, psi of r is proportional to r to the power of L when r is small, which means that you don't have a chance to find these electrons very close to the nuclear core if you have a very large orbital angular momentum. But this is expected because in the classical mechanics, you know this is typical effect from this centrifugal repulsive barrier, Li-Xin-Li. Okay? If you have a very large orbital angular momentum, so if you have a classical object, and you could just use a central force to make this classical object moving around a z-axis, so you have a very large angular momentum along the z-axis. So in such a case, this particle feels some kind of a centrifugal force, which keeps the particle from actually collapsing. So particle is always having the distance r to this origin. Okay, so the particle would not collapse to origin if you have a very large orbital angular momentum for classical matter. Here is the same thing. So suppose you have a very large angular momentum. This probability of these electrons in a small radius limit is really, really tiny, because this is increasingly smaller and smaller for increasing L. This is an effective centrifugal repulsive barrier that keeps the electrons coming closer to the nucleus core. just like a classical object with a very large angular momentum, that this object is always staying at finite distance away from this origin. So that's one property of the psi of r. The second property is the bumps of humps of this polynomial h function. So in fact, you could show that this h polynomial is a polynomial of degrees n of r, which is given by n minus l minus 1. So this tells you that there's nr nodes, or zeros, or n minus l bumps in the probability distribution. So let's just make some plots of this probability distributions of this in the radius direction, and you'll see there's some up and downs, nodes and bumps, which corresponds to the maximum or minimum value of this probability distribution. Suppose L is actually n minus 1, capital R, and L is actually n minus 1, which is, we just look at this probability distribution for a particular case when L is actually n minus 1. So in that case, you could very easily see this bumps and nodes from this minima or maximum value of this probability distribution function. So in other words, if you make a plot of the probability distribution, P of r as functions of distance or radius, you may find there's some minimum and maximum value of this probability distribution. If this probability distribution hits 0, we call it a node. But on the other hand, if there is a maximum value reached at some point, we call this bump. So in general, you can imagine that for this polynomial of h function with the degrees of n of r, there are in general many nodes, but in this particular case, it has nr nodes, n minus l bumps. So the number of nodes and bumps are determined by this kind of derivatives of this distribution function back to r, and you make it 0, and this determines the minima or maximum value, which means that determines the nodes and bumps of this function. In this particular case, when L is actually n minus 1, you figure out this condition to have the extrema, or minima or maxima value of the probability distribution, and you find that this is a distribution only gives you one peak or one bump. This is one bump. However, if you calculate or plot this P of r for a smaller value of L, you get more bumps. So what does it mean? So what is the importance of this bumps, number of bumps? Well, the number of bumps refers to the radius of this orbit, so-called orbit, that you can have. So if you have only one bumps, so if you have just one bump, which means that you have only one orbit or one radius, which means that your probability distribution is more like a circular orbit. However, if you have more bumps, which means that you have the maximum probability that you can find this particle circling around with a particular orbit with some radius, if you have two bumps, which means that you have two possible radius, okay, with the maximum probability, which means that your orbits may be more like an ellipse, because you know that for elliptical shape of the orbits, you have two possible radius. This radius R1 and shorter radius R2. The less bumps makes this orbits more circular, and more bonds make this more like irregular shape or elliptical shape. For this last bound's case, that the orbit looks more like a circular, this is precisely this Bohr's assumption, that the electron is circling around the nucleus coils by a circular orbits. And you know that this is not true because in general you get many possible orbits with different radius, so that the shape of these orbits no longer circular, very messy, complicated orbits. Okay, so let's end our lecture now, and we'll continue finishing this part of this hydrogen atom next time. So I'll see you next Monday.